All right, now I'm going to bounce back to, I want to link up the ideas of measurement and confidence intervals. This introduces an important thing to understand. So normally when I teach this course face-to-face, and I teach the postgraduate course as well, there's a little exercise I do in class where I usually have students sitting in 7 or 8 groups, and I get each group to send forth their 2 members with the best eyesight, and I give them a wooden ruler like this one here, except the one I give them is, something I've had lying around the house for 20 years. It's kind of chewed up and, pretty hopeless. And then I get them to measure this little thing here, which is a beer bottle opener. It's a thing you attach to your key ring and you use it to open beer bottles. So I get them independently so they don't get to talk to each other, and each person has to sort of measure it and then write the number down on a piece of paper and give the piece of paper to me. So I get, in this case, there were 7 groups and I got 14 measurements. And these students, their average age was about 36 or 37. So some of them would have been a bit past their prime with eyesight. And I had previously measured the thing myself with some pretty accurate calipers like this, so I knew what not the exact length, but I knew with much greater accuracy than they did what the length of it was. So this is what the data looked like. So each student gave a measurement. There's a little box plot there. As you can see, it's not a typical garden variety box plot. There's no upper whisker. Basically all the measurements were either 6.3, 6.4 or 6.5. And what we did, you can look at the table or even the box plot really, and you can work out what the interquartile range and the median is. It's pretty obvious. The median's the thick line on the left side there is 6.4, and then Q3 is 6.5, and Q1 is also 6.4. Okay, so the median and Q1 are the same. And there were 14 measurements. So we've got all the data we need there to estimate a confidence interval. So we do that using the formula, IQR over 1.8 times the square root of n, to get the standard error. So we've done that several times now. And we get an answer. So the standard error is 0.025 centimeters. And then we calculate the confidence interval. So the lower bound is the median minus 1.96, that's the critical value, times the standard error, that's 6.35. And the upper bound is 6.4 plus 1.96 times 0.025, which is 6.45. So that's the confidence interval. And so we can say that we're 95% confident that the true length of the beer bottle opener is between 6.35 and 6.45 centimeters, and we commonly write that by putting those things in square brackets with a comma between them. That's a typical way we write a confidence interval, like that. Now, the measurement that I had, which was using a device that was supposedly accurate to about 1/4 of a millimeter or something, was 6.41 centimeters. So that's well and truly in the confidence interval. And I also bootstrapped that data to work out a confidence interval, and there's a footnote there, you can look it up. That estimate is actually really good. And that's notwithstanding the fact that this sample is not normally distributed. So the other way that commonly people would do this is they would use a t-test to estimate a confidence interval for the mean. That would be perhaps a little bit questionable, and probably okay, but with t-tests you're supposed to be able to claim that your sample is plausibly drawn from a normal distribution, and I'm not sure that you'd necessarily be able to make that claim with a box plot that looked like that. Okay, there's not going to be any test questions about normal distributions. I keep mentioning this stuff about t-tests and normal distributions and things because quite a few students in the class have already studied that stuff, and I'm just trying to help them triangulate the things I'm talking about with the things that they're familiar with. Now, there's another way that a kind of confidence interval is expressed that you will come across typically with physical measurements. The practice is not entirely consistent, but a typical sort of thing you'll see looks like this. So people would report this result as saying, why have I put 2.4? That probably should be 2.5 there. That should be a 5, sorry. Let's say the length of the bottle opener is 6.4 centimetres plus or minus 0.025 centimetres. So the thing that goes after the plus or minus is the standard error. And I think I have mentioned to you once already that if you use a critical value of 1.96, you get a 95% confidence interval. If you use a critical value of 1, in other words, you just have the median plus or minus the standard error, you get a 68% confidence interval. So just kind of be aware of that. You will see this from time to time. The problem is that I did a bit of searching around today, just looking at various industrial sites and sites of people that sell measuring equipment and so on. The practice is not entirely consistent. So when you see something like that, you probably want to just check what it actually really means. But a fairly common practice is just to report the standard error in that way. All right. Now let's just think about the population and the sample here. So, because this is an important one to know about. So with physical measurements, when you do something like this, the way you think about it goes something like this. I set up a measurement procedure, or you could think of it as a measuring instrument. The measuring instrument involved 14 people using a fairly hopeless old wooden ruler to measure this object. Now, the measurements that resulted, the 14, would be thought of as a random sample or a representative sample from an infinite number of possible measurements that could be made using that procedure. So this is one of those cases where the population is kind of hypothetical. Okay, it doesn't actually exist. But the idea is that the procedure is taking a random sample from this potential hypothetical population. And then once we've done that, we can calculate a standard error, and we can use it in various ways, including to produce confidence intervals. So this is a feature of measurement more generally. Any kind of physical measurement, that's how we conceptualize it. It's also a feature of latent construct measurement. So, for example, after I marked the last test, the test is measuring a latent construct, which is your achievement of certain learning outcomes. You all got a score. I can calculate a standard error of measurement for that score. I can calculate a standard error, and I could tell you, I'm not sure that I will because you mightn't be too happy, but I could tell you what the confidence interval, 95% confidence interval is for your mark. What I can say, and actually in the case of that test, the numbers were pretty good, but if you run an exam and you mark it very carefully, you've got a good chance of getting a standard error of 5 marks. And that standard error of 5 marks is the reason that we have a grade of PX, which is if you get 45, between 45 and 50. The reasoning is, well, that 5 marks is sort of within the standard error range, and so we give the student the benefit of the doubt. We let them do some supplementary assessment, and if they pass that, then they pass the course. That's actually originally the rationale behind it was you can calculate standard error for tests, and this is done as a major part of quality control in high stakes tests like the HSC in New South Wales, the Gaokao in China, and so on. When the results from that are being processed, and even when they're training the people who do the marking, they measure the standard error of measurement of the tests. So we can do that with latent variable measurement with the sort of questionnaires that psychologists use, and so on. We can do it with IQ tests, for example. The standard error of measurement typically is about 3 IQ points. So your 95% confidence interval, if you've ever done an IQ test, the 95% confidence interval is going to be about 6 points either side of the score that you were given. So I think for those of you in Canberra, that I think some of you probably have during your schooling did NAPLAN tests. I think in the NAPLAN test reports they might actually show the standard error. They probably call it something else, but I think they put some kind of indication of the error around the scores as well. So we can certainly do that with latent measurement. So let me say a little bit about some of the terminology of measurement. So the measurand is the thing that's being measured, and that's something in the real world. Okay. And there's a question about whether, when you're doing a measurement, whether you're actually measuring the measurand that you claim to be measuring. Now, often that's fairly straightforward, but even in a case where you're holding a ruler up against a physical object, there are things that can affect the measurement that are not the thing that's being measured. And so in the case that we've just looked at, that could be things like, the eyesight of the people who are doing the measuring, the quality of the ruler, a failure to take into account parallax error, and so on. They can all affect the what we call the trueness of the measurement. So trueness is a term that comes from the International Standard on Measurement, the ISO standard. And to summarize the story there, the accuracy of a measurement is made up of 2 components. One is the trueness, is the measurement actually measuring the measurand it claims to be measuring, and the other is precision. And precision is what we measure with standard error. Okay, it's got to do with, if you kept repeating the measurement, how close would the measurements be to each other? Essentially, that's the idea. So with physical measurements, we use this terminology, trueness and precision, and together they are the components of accuracy. So there's a little diagram here this sort of diagram is commonly used to illustrate this concept, or these 2 concepts. Let me see if I can get that in the center there. Okay. So in the bottom cut, so this is, you imagine somebody shooting a target or throwing darts at a target or something. So what you have in the bottom left-hand corner here is you have low precision and low trueness. Okay, so we'll say they're bullets. The bullets are not hitting the target, so that's the center of the target there. The bullets are not hitting the target. They're off to one side and they're scattered all over the place. Okay, so they're not very consistent in where they're going. And then here in the bottom right, you've got high precision, so the bullets are all going to about the same place. It's just the wrong place. Okay, they should be going here. Up here you have relatively high trueness, so the bullets are all centered around the center of the target. So they're sort of hitting the measurand, but they're scattered around the place, so there's a lot of error there. And then up in the top right-hand corner, you've got high precision, so they're all close together. They're all hitting about the same spot, and the spot they're hitting is the actual center of the target. It's the measurand that you're trying to hit. So those are the two kind of theoretical components of accuracy. Now, a lot of people use terminology which is not ISO terminology. So to make things confusing, they will use the word accuracy to mean trueness, but precision means precision. So just be aware of that. I'm sorry I have to keep apologizing about terminology, but honestly, it just keeps being a nuisance. All right, so that's trueness and precision. So that's terminology that is mainly used in the physical measurement world.